Hello, students. I'm trying something new. We're going to start with the first section of our first chapter called The Particle Nature of Matter. First off, just a brief definition of science. Science is just the knowledge that we get from testing our natural environment, things in our environment, to discover things about our environment. Chemistry is specifically the science that deals with the study of matter. When we talk about matter, we're really referring to the atoms, okay? What makes up stuff, if you will. What is a substance? A substance is, when I say that in a lecture, I'm just referring to a chemical, because this is chemistry class. Okay, so it just has, a chemical is just something that has a very definite and uniform makeup, its composition. Matter is anything that has mass and it takes up space. So even things like air in the room around you, the air is matter because it does have mass. It's made up of atoms. It actually does have weight, believe it or not, and it does take up space. Not a whole lot of space, but it does take up space. Okay, an atom is just the smallest particle that is still the same thing, the same element, the same substance. Okay, if you start changing that atom in any way, if you start adding particles to it or removing particles from it, it is no longer the same thing. Most of an atom is just made up of empty space, and most of the mass is in the nucleus. It has a very dense nucleus where most of its weight or its mass is, and the rest of it is predominantly empty space. Okay, an element is just a pure substance that you can't make any more simple. So think of an example here, silver, like the picture. If you have a block of silver and it's pure silver, that means every single atom in that block is an atom of silver. Okay, and every one of these elements has its own abbreviation or its own symbol on the periodic table to identify it. Little biology tie-in here. Most abundant elements in the human body. Okay, the four biggest ones are oxygen, not surprisingly, carbon. That's why you hear on the sci-fi programs and they say carbon-based life forms, because in our world, all life is very carbon-based, so that's what we know. Hydrogen and nitrogen. Nitrogen is a big portion of DNA, for instance. Then we have a lot of little bitty pie pieces there, some magnesium, sodium, calcium, some other stuff. Those are what we might refer to as electrolytes. You will go drink a Powerade or a Gatorade to replace your electrolytes. Very important for the functioning of the body, but you notice in very tiny quantities compared to the other stuff. Okay, but if it's off just slightly, your muscles may not work right, your nervous system and brain may not work right, so you could be in trouble. So the body really fights hard to keep those at very specific quantities in the body. Okay, perhaps you can tell from looking at this what the most abundant chemical is in the human body. So these are the most abundant elements. What is the most abundant chemical? Anybody come up with water? H2O? Okay, what is a compound or a molecule? We use those interchangeably. A molecule is technically a very specific type of compound, but sometimes we get lazy and we just use those as the same term. A compound is just a substance that has a fixed ratio of different atoms. So like when I wrote H2O, always has 2 hydrogen and 1 oxygen stuck together. Okay? We can break apart, unglue, if you will, those atoms and rearrange them in different ways. That's essentially what chemistry is. Okay, we can combine 2 of the same elements. We can do 2 different elements. We can do 3 or more elements. Okay, these are all compounds. Okay, so when we start talking about how atoms behave and what atoms do, one of the things that we have to understand is a little bit about energy. Now, energy is very important to chemistry, but also when we do some of this talking about energy, we're technically crossing over into the physics realm already. So we're in chapter 1, we're already talking about biology and physics as well. So what is energy? No one really actually knows what energy is. It's one of those things we all kind of intuitively know, but if you had to define it, that's very difficult. We measure energy in joules, not like your diamond ring joules, but Joules, joules. Okay, a joule is a derived unit, just like density is a derived unit. Joule is a kilogram meter squared per second squared. It's very odd looking. And sometimes if we really have to provide a definition for energy, we will say it's the ability to do work, the ability to make something happen, the ability to change something. That's kind of how we would define energy. Okay, there's some different categories or types of energy. One is potential energy, the energy of position. Okay, so you can see this here, the weight on the pulley where it says PE. It has a lot of potential to have energy when it's suspended there up high. Or the girl throwing the ball, the first diagram there, the ball has a lot of potential when it's up really high. Kinetic is the actual energy of motion. So when the weight is falling and hitting that post, or when the girl drops the ball or throws the ball off of the cliff there, now those items have a lot of kinetic energy or energy of movement. Okay, objects can have potential and kinetic at the same time. Okay, a little chemistry tie-in. Potential energy is stored in the chemical bonds that hold atoms together. So the glue, or the things that actually hold the different elements, the different atoms together, if that glue is broken, let's put it that way, then energy can be released. And this is how we get energy from food. So the food we eat, when we digest the food, it actually breaks some of those chemical bonds in between the atoms. And then we have ways our body, you've probably remember this from biology, that we do things like store ATP, which is a chemistry molecule that's an efficient way for our body to store energy. Plants do this too. They get energy from the sun, and then they convert that using chlorophyll and store that as energy. So this is all, if you really get down to the substance of what is happening, this is all chemistry. Okay, here's our kinetic energy, our energy of movement. An atom, just to let you know, is never still. It's always moving. The particles in the atom always have some sort of movement. There is some basic mathematics that you can do to calculate movement, and it has to do with the mass of the object and its velocity or its speed. So obviously this is a little bit different when you're calculating kinetic energy of atoms, because the mass of an atom is incredibly, incredibly small. So you're going to get some very tiny numbers if you do the calculations. And then we also have thermal energy, which is another energy that we use a lot in chemistry. Thermal energy is really talking about the kinetic energies, or the energies of the movement of the particles. Okay, so the faster the molecules are moving, the warmer, hotter, we would say that substance is. And the slower they're moving, the colder it is. That's kind of how we define hot and cold. Okay, there is something in chemistry called absolute zero or 0 Kelvin, where the particles quit moving. Atoms completely stop moving. We cannot do it. We have not been able to achieve it. The problem is that to cool something off, you have to take that heat or that particle movement and transfer it something else. So if you're almost down to 0 movement, there's nothing that's lower movement that you can transfer that movement to. So we have not yet figured out how to do absolute zero to achieve it, and there's all kinds of theories. People say, oh, we'll invent time travel, and there's just all kinds of theories. What would happen? Nobody knows, but what would happen if we could completely stop the movement of atoms? We're not able to move any longer. Okay? So we're normally measuring thermal energy as temperature quite a bit in science in general. Okay, so here's a diagram where it's trying to show you that in the fire, the molecules of the metal are moving very fast, which is why you heat up the metal to be able to bend it or shape it, do something to it. And then under normal circumstances, the metal atoms, they're moving, they're vibrating, there is some movement, but it's very small. So that's why solid metal stays solid. Okay, here's another way that we can't see this with our eyes, but we have all kinds of instrumentation now that can detect thermal energy, which is literally the movement of the particles in the atoms. And so here you can see a thermal imaging radar gun here showing heat signatures of different buildings. And that's all I have for today. Thank you for joining me.